Radio astronomy has been at the forefront of astronomical observations since its advent, but one telescope can only do so much. Hello, I am Sohini, and today I am going to talk about the exciting technique that helps astronomers image the sky in stunning detail and explore new frontiers of the cosmos. Very long baseline interferometry, or as it is known more popularly, VLBI. Before I dive into the details, I would like to give a quick overview of the content I am going to share today. Firstly, I will talk about the brief idea behind VLBI. Then we will proceed to see how it works. Next, we will explore the several different types of VLBI arrays in the world, and finally, we will talk about what the future holds for this field. The first and most obvious question is, what is VLBI? What is the logic behind this technique? The very basic idea is as follows. An array of radio antennas spread over thousands of kilometers is used to observe one particular radio source. The data is collected from these telescopes around the globe. The signal is combined at a central location. This effectively gives us a telescope thousands of kilometers in size. Sometimes the size of the telescope can be Earth-sized. This is absolutely impossible for traditional telescopes. Now let us talk about how this method works. So as I mentioned before, firstly the data is recorded at each telescope, and an astronomical data is time-stamped with outputs from atomic clocks such as hydrogen masers and is combined with a GPS timestamp. Then the recorded data is transferred to a central location. The data is played back and synchronized based on the outputs of the atomic clocks. A range of nanoseconds is chosen, and then the data is played back till the correct timing is found. Signal delay due to different distance from radio sources has to be managed artificially. So this delay is added before the final result is stitched together. VLBI has developed over decades, and now several different types of it are used around the world. Let us see what those are. The first and the most obvious one is the ground-based VLBI. Here, obviously, all the antennas are based on the ground. It is the most used form of VLBI even till this date. The most popular array out of in this category is probably the Event Horizon Array or the Event Horizon Telescope. This telescope has 8 antennas in the array. It famously imaged the Messier 87 star, the supermassive black hole at the center of Messier 87 galaxy. Now it is attempting to test Einstein's general relativity by studying Sagittarius A star, the supermassive black hole at the center of Milky Way galaxy, and matter accretion around it. The next prominent array is the European VLBI network, or more popularly known as EVN. It is made up of 22 telescopes spread out across Europe, Asia, and Africa. So despite its name, its size is actually much larger than continental Europe. The next most popular array is the VLBA network. It is spread out across the continental US. It consists of 10 25-meter antennas, and it is spread out across 5,351 miles or 8,612 kilometers. When the EVN and VLBA network from the US work together, they give us the global VLBI. The global VLBI provides even better resolution than provided by EVN or VLBA individually. It falls into two categories: global 3 mm VLBI, known as GMVA, and the global centimeter VLBI. The next category of VLBI is space VLBI. As the name suggests, When ground-based arrays are connected to telescopes or antennas on satellites in the orbit of Earth, the combined setup is called space VLBI or SVLBI in short. Now the obvious question is, why do we need SVLBI? The most important reason behind the advent of SVLBI is the limit on the baseline of ground-based VLBIs. This limit is imposed due to the finite size of Earth's diameter. Due to a limited baseline, we can only get a limited resolution from ground-based systems. At 5 GHz, the best resolution we can get from ground-based system is only about 1 milliarcsecond. At this resolution, many radio sources remain unresolved or can only be resolved partially. So, the most straightforward way to increase baseline is putting one component into orbit, and that is exactly what SVLBI does. SVLBI is capable of imaging the sky in micro-arcseconds. So this is obviously orders of magnitude better than ground VLBI system. Dedicated satellites have been placed into orbit around the Earth for the purpose of SVLBI. The first such dedicated orbit was the Highly Advanced Laboratory for Communications and Astronomy, also known as HALCA in short. It was launched by Japan in 1997 and it ceased operations in 2005. It carried an 8-meter dish on board and it was a part of the VLBI Space Observatory Project, or VSOP for short. Next we have the Russian Spectre R. It consisted of a 10-meter dish on board. It was launched in 2011 by Russia and it stopped working in 2019. It worked with a project known as Radio Astron. It was placed in a highly elliptical orbit of about 10,000 kilometers at apogee and 338,000 kilometers at perigee. It made Radio Astron, the project it was working with, the largest VLBI system in the world. It provided a resolution of 8 microarcseconds, which is really quite unbelievable. Next we have the category of eVLBI. eVLBI is a recent development. It basically uses fiber optic technology to almost instantly transmit data from radio telescopes to the correlation center instead of recording at the site of observation. So traditionally, data was recorded at the site of observation, that is at the antennas, in magnetic tapes. These tapes would have to be then physically transported to the central location where the data was supposed to be correlated. The entire process would take weeks. Now, with the use of fiber optics, this process has been simplified and shortened, and the time difference between observation and analysis of observed data is almost negligible. The central processor correlates the data in almost real time. The data is available for inspection to the astronomers almost immediately. Hence, it is the obvious choice for studying transient events like supernovae and gamma ray bursts. This also enables us to launch follow-up observations very quickly. It is also easier to organize the data once the procedures have been made clear. Hence, due to the advantages of this technique, it could become the standard way of doing VLBI in the future. The most notable array using this technique in the present time is the European VLBI network, or the EVN. We have talked about the wonders of VLBI, but now let us see some scientific results of the process and what they are used for in actuality. These are some of the important scientific uses of the VLBI technique. As you can see, it is used for other purposes apart from observing distant radio sources, which is of astrophysical importance. So, of course, the most important, the most relevant use for VLBI for us as astronomers is observing distant cosmic radio sources and imaging supermassive black holes and testing general relativity, etc. Apart from that, it is also used for geodesic purposes, which is done by observing distant radio sources like quasars over a period of time and taking multiple measurements and using those measurements to make these geodesic calculations. It is also used to define the celestial reference frame and maintaining the terrestrial reference frame. VLBI can also be used to improve atmospheric models and study the nearby stars at radio wavelengths. This is an example of a radio source that was imaged using the VLBI technique. It is the NGC 3341 minor merger. A nearby disturbed system at a redshift of almost 0.027. It is a merger between a giant disk galaxy and two low-mass dwarf companions within the galactic disk. So spectroscopic data confirmed the physical association, but investigation on the presence of a supermassive black hole was missing. The data from Chandra, SDSS, EVLA were combined, and then the European VLBI network was used to make observations at 1.6 GHz and 5 GHz to explore the nature of components of NGC 3341. The high angular resolution provided by EVN helped the astronomers to resolve the radio emissions seen with VLA previously, and it was found that the nucleus of the galaxy is actually a star-forming region. So as you can see, the data on the left is the SDSS data. It is taken in the optical band. The image in the center is an X-ray image from Chandra, and the image on the right is a radio image, which is a combination of VLA and EVN data. This is obviously one of the many radio sources that have been imaged using this technique, and it is actually one of the most important astrophysical uses of VLBI, which is imaging radio sources at better and better resolutions. This is obviously the famous image of the black hole at the center of the M87 galaxy, known as M87 star. This galaxy is in the Virgo cluster and it is almost 55 million light years away from Earth. It is the most powerful radio source in Virgo cluster. That is, the M87 galaxy is the most powerful radio source in the Virgo cluster. It is also a very powerful X-ray source, which suggests a presence of hot gas in the galaxy. Also, a luminous gaseous jet projects outward from the galactic nucleus at an angle of about 260 degrees. This black hole that was imaged is actually a supermassive black hole, and it has a mass of about 6.5 billion solar masses. It was imaged back in April 2019, and it was a big deal both in the scientific community and in the non-scientific community, because it is the first optical proof of a black hole that we have obtained ever. So it is the first visual image of a black hole. The ring, as you can see, is brighter on one side because the black hole is actually rotating, and thus the material on the side of the black hole turning towards Earth has its emission boosted by Doppler effect. This image was taken at 230 GHz, which corresponds to a wavelength of 1.3 millimeter, and the astonishing part is that the angular size of the black hole is actually 38 microarcseconds. This size would have never been, this resolution could have never been achieved without the use of VLBI. So this image that you see today is possible only because of the presence of VLBI technique. Now let us talk about the future of VLBI, since it is clearly a very developing technology. These are the important future plans in the VLBI technique. More SVLBI projects have been proposed to extend the baseline up to 350,000 kilometers. So in these future SVLBI projects, what has been proposed is that two or more than two components would be launched into the orbit so that the baseline can be extended even more and the resolution can be even sharper. East Asian VLBI network is an important ground-based array that is being set up. It is shown in the figure on the right. Adding mid KAT and SKA1 mid as VLBI elements has also been proposed, since both these telescopes can be tuned to serve as VLBI elements. Making eVLBI more robust and commonplace is also a priority in this sphere. As mentioned before, eVLBI simplifies the process of VLBI a lot, and hence could be a standard way of doing VLBI in the future. SKA2 is planned to have thousands of kilometers of baseline throughout Africa, so it will be Africa's own VLBI array. To conclude, we have discussed about the idea behind VLBI, that it increases the size of the telescope that we are using hundreds of folds. Then we discussed the method used to study distant radio sources using VLBI. So in brief, the method was that data was collected at each telescope, it was recorded and then sent to a central location for correlation. Nowadays, fiber optic is used for this purpose, and the system has become even more streamlined, and data can be analyzed almost in real time. Then we discussed the types of VLBI, namely ground-based VLBI, space VLBI, and eVLBI. Ground-based VLBI has an array where all the components are based on the ground. In the space VLBI system, one or more than one component is in orbit, that is in space, and in eVLBI, the fiber optic cables are used to transfer data. Then we discussed some scientific results and some important uses of VLBI. The ones of astronomical importance are resolving radio sources and imaging supermassive black holes and testing Einstein's general relativity. Then we talked about the future of VLBI and the upcoming arrays that are being set up right now. These are the references listed here. All the websites have been hyperlinked in the PowerPoint presentation that I will share. I would like to conclude my talk with that, and thank you for your time.